Good day, Tri-City Geometry. Let me start off with a word of prayer. Father in heaven, continue to be with us during these challenging times. Help us to persevere through the end of our last few weeks of our school year. Thank you for everything we've been able to learn. Help us to be faithful in retaining it and using it to show love to you and to our neighbor. Bless us in this lesson today. Help us as we seek to finish this chapter before the end of the school year, and help us to be diligent in all the work that we're seeking to accomplish. In Jesus' name, amen. All right, so we're transitioning from surface area now to volumes in our study of three-dimensional figures. And if you look at this picture on page 421, basically section 9.2 was, how would we paint the outside of these cylinders? And now we're going to ask, how would we fill them up with oil or whatever it is that we're doing here. So that's what we're about here. First, we're going to review a little bit with a lesson opener. Given a cube, and of course, a cube has 6 sides, with an edge of 5 inches, find each value: the area of one face, the total surface area, and the volume. So please pause the video and write these down real quick. You got 5 inches for an edge, area of one face. So the area of one face would be the side squared, right? The edge squared, 25 inches squared. How about the total surface area? Well, we got 6 surfaces, so we just take that area of one face and multiply it by 6. So that gives us 150 inches squared. And then the volume is a cubic measure, right? Instead of a square measure. So it's the edge cubed. So it's a smaller number than the total surface area, but of course we're dealing with cubic units, so it's actually a much greater content, if you will. So that's just a little review as we're getting into it. And so, as I said, we're transitioning from surface area, which we did in the last 2 sections, to now talking about volume. So if you look at the diagram here on the right, you'll see that we have ways that we measure the edges or the sides, if you will, and we use that to generate cubic units. A cubic unit is a cube whose edges measure 1 unit. So for the left one, obviously the unit would be centimeters, cubic centimeters, centimeters cubed. For the right one, it would be cubic yards. And in science, we do end up using a lot of metric measures. So when you're in a college and a laboratory, you'll use a lot of metric measures. But when you're kind of out in the real world, in America at least, you'll be using more cubic yards. All right. The volume of a solid is the number of cubic units needed to fill its interior completely. So the volume of one on the left would be 1 cubic centimeter, 1 centimeter cubed. The volume on the right would be 1 cubic yard. It's length times width times height. We'll get into that here in a second. So here on page 422 is your postulates. The volume postulate: every solid has a volume given by a unique positive real number. Okay, every solid has this. And just like distances are always positive, even if you're going to the negative number on a number line, you're always going to have positive numbers here. Okay. Volume of a cube postulate. The volume of a cube is the length of one edge cubed. Okay. So this is what we're going to use as kind of our standard in which to measure all other prisms. Okay, prisms or cylinders. We're going to use the cube as the standard because we measure things in cubic units. Okay, So we take one edge, for instance, the 5 inches of the cube that we had at the beginning, we cube it, and that gives us our volume, capital V. The volume addition postulate, if the interiors of two solids do not intersect, then the volume of their union is the sum of their volumes. So if you look at this puzzle here at the top of page 422, it consists of 27 cubic units. And if we just looked at the different cubes, we would be able to add all of these together because they don't intersect. They're simply, they simply touch each other. And so you could add all these together to get the total of the 27 that you have here in this larger cube. So you've got these smaller cubes, you're putting them together. The volume addition postulate is what allows you to do that. Congruent solids postulate. Again, this is just sort of like congruent triangles, congruent polygons. Congruent solids have the same volume, just like congruent polygons have the same area. Congruent segments have the same distance. Okay, so this is all just flowing. We're just adding dimensions more. All right, so if we look here at this, we can see that we have a length on the left, we have a width on the right, and we have a height on the upper right. And so, if we think about that principle of an edge cubed, well, here we've got different length edges, but we're still going to do the same principle. We just multiply them all together. So we can see that the bottom one has 4 by 3, so it's going to have 12 units. And then you're stacking them, so that means we're going to have 12 times 6, which gives us 72 cubic units for this prism. Now we can have right prisms in which the height is going to be one of the edges of the prism, or we can have an oblique prism, in which case the height is not necessarily going to be equal to one of the edges, but you would have to use potentially the Pythagorean theorem to find out what that height is. Okay, but you're still going to use the same formula, length times width times height. You just need to realize that with the oblique one, the height is not necessarily one of the edges on the prism. You may need to calculate it. And then also notice the shaded area here is a cross section. We've talked about cross sections previously here. And what the cross sections help us do is to help us see that the volume is going to be consistent because these cross sections are the same dimensions as the two bases, right? The base at the top and the base at the bottom. And the same thing is true with the oblique. The cross section here that is parallel to the bases is going to have the same shape, and so that helps us to see the consistency of the volume throughout this. So this leads us to a theorem about cross sections. A cross section of a prism that is parallel to the bases of the prism is congruent to the bases. And part of what this would allow us to do, for instance, is if we wanted to pretend that cross section was a solid unit that would sort of stop it from filling up any further, we'd be able to kind of calculate how high that cross section was and be able to figure out a proportion of a portion of the prism that we wanted to find the volume of rather than the whole thing. Cavalieri's principle is found here on page 423. For any two solids with the same height if all planes parallel to a fixed plane form sections having equal areas, then the solids have the same volume. So let's say that again. For any two solids with the same height, if all planes parallel to a fixed plane form sections having equal areas, then the solids have the same volume. And this is what allows us to derive our formulae for the volumes of cylinders and prisms. Okay, so it's an important principle. And it leads us to our theorem about volume. The volume of a rectangular prism is the product of its length, width, and height. So go back and think about that one we just looked at on the previous page. 4, 3, 6. 4 length, 3 width, height of 6, which gives us 72 cubic units of volume. And so another way to state this is to combine the length and width into the base area, right? So this capital B, you remember from the previous two sections, is the area of the base, okay? If it's a regular base, then it's just going to be one edge squared. But if it's not, it's going to be length times width. So the volume of a prism is the product of its height and the area of its base. Okay. And again, you may have problems in the homework where you're given the volume and you're given something related to the base and you've got to figure out the height. Okay. So it's not always that you're going to be given B and H and you got to find V. Sometimes you'll be given B. So you've seen this before, right? This is nothing new. So find the volume of the regular prism. So again, let's remember what our formula is. Volume is base times height. So first we've got to find the area of the base. So what's the area of a hexagon? Well, again, let's remember that a hexagon is 6 equilateral triangles. So the formula for an equilateral triangle is square root of 3 divided by 4. And so if we have 6 of those, and we know what one of the sides of the equilateral triangle is, which is what the sides of the hexagon are, 8 centimeters, then we can find that B, that area of the base, and then all we have to do is multiply that. So we plug in the number 8, we reduce the 6/4 to 3/2, right? That's the area of a hexagon. And that comes out to 96 times the square root of 3 centimeters squared. So there's our B. So here's our overall volume. So now we just have to multiply it by H. So that's 14 times the square root of 3. So the square roots are going to get rid of each other. And our total is going to be 4,032 cubic centimeters. Okay. So we knew that the area of the base was a square unit. We're adding a dimension, not literally adding, we're multiplying, right? A dimension which is going to give us cubic units. So 4,032. Now we move from, on page 424, from prisms to cylinders. Again, just like a prism, two bases. And again, we may have a height that is not the edge of the cylinder. If it's oblique, okay, think of the Leaning Tower of Pisa, right? Leaning Tower of Pisa would be an oblique object. But again, the same formula, the area of the base, capital B, times the height equals the volume. So the volume of a cylinder is the product of its height and the area of its base. In a circular cylinder, the volume equals pi r squared, right, the area of a circle, times the height. So again, pause and repeat that a couple of times. How many cubic inches of sand are needed to fill the cylinder? So we need to find the area of the base and then multiply it by the height. So again, the overall volume pi r squared, the area of the base, times the height. So we plug in the numbers. That's going to give us 300 pi inches cubed. Always make sure you're putting that cubic mark. And when we multiply it by 22/7, we get approximately 942.5 inches cubed. Now here is what I said earlier. If you're given the volume, 22,000 cubic feet, and you're given the diameter so that you can figure out the area of the base rather easily, what is the height of corn that you could fill? Okay, if you got 22,000 cubic feet. So look at the picture here of the silo. I used to live in Iowa, excuse me. And Iowa is full of huge corn farms, soy and corn hogs. And so we would see these huge silos everywhere. Ohio, where I grew up, is similar. It's the 6th largest agricultural state in the country. So anyway, if you had 22,000 cubic feet of corn, and I'm sure that's what they sell it as, right? Bushels of corn, right? So again, here's our formula. And so in this time, we know the total, and we can easily figure out the area of the base. And so we need to divide that out. So we're going to divide 100 pi into 22,000, which is going to give us 220 over pi feet. Again, if we do 22/7 or multiply by 7/22, we'll get approximately 70 feet. So you would fill 70 feet. That's a lot of corn. But that's what these huge farms out in the Midwest produce. So that's it. I'd like you to do 2 to 24 even, and then I'd like you to do 34 and 36. So 34 is interesting because you have to find a prism volume and then subtract the cylinder volume to find out how much greater the prism is than the cylinder. And then we got a cool question about filling up a pool. As we're getting into warmer weather, that might be something that you're thinking about. And then we have some review of area formulae in the review. Okay, so this will be due end of the week, and then you'll also do your quiz this week, which will be due next Tuesday. So if you need me, I will have very limited access. I'll be away on a trip this week. I might be able to get an occasional email. But anyway, Memorial Day is when I'd like to see this stuff in. Okay? All right, bye-bye.